right. Well, my name is Emily Estes, and most of you probably know that. And I want to talk about algebra for programmers today. And so this is the FunctionalKnox meetup, and there's a lot of connection to functional programming. And so have some goals. For one, there's a lot of algebra stuff that shows up. Some of it is stuff we learned in high school, and we, well, some of us might have learned it in high school, some of us might not remember it. It applies very much to programming, but when you're a high school student, you rarely realize this, and to see it actually applied to programming, so I want to do some of that. There's a lot of terminology that shows up when you read functional programming literature, and it can be very overwhelming and confusing. Some of it is actually really, really straightforward. Some of it's a little less, but all of it is pretty easy to take apart. There's this famous quote that, a monad is just a monoid in the category of the end effectors. What's the problem? If you understand all that, that's like, oh, obvious. And if you're not, you're like, why am I doing this? Want to go in some of that, and also want to have a little fun. So I've got a question. How do you write a big program? You guys can answer if you want.
Always write just one big ball of it and just let the next guy deal with it.
That sound good?
Form 1.
Actually, no, I just renamed it to main form.
So my answer to this question is by combining smaller programs. I mean, is that controversial for anyone here? No. And the next question is, well, how do we combine little programs with more programs? Now you're going to say, well, wait a minute, what's a program? Well, this is the functional programming talk. So I could go into this long speech about the lambda calculus and the equivalence of Turing machines and some computability theory, but you guys will probably mutiny on me. So we'll just say it's a function. So a program is a function. So we can use, we'll use functions to combine programs. So let's see. So I have an example here. This is a multi-threaded program. I wrote it in Java, so obviously it's wrong. The example I decided is I have this counter, and I want to actually have two counters, and I want to move numbers from one to the other. And since this is multi-threaded, ideally we would like to see that another piece of code interacting with this will either see the same, like, if we've got 5 in one and 10 in the other, we won't see a situation where we've got like 4 and 10, it'll either be 5 and 10 or 4 and 11. And this might seem a little trivial, but, if you've got like a queue, a work queue of some sort, and the first queue is jobs to do, and the next one is, jobs finished to pass on to the next stage, this is not unreasonable. So I've got my counter. And I've got this drain here, and so it locks the source, and then it locks the drain, or the sink, and then it moves it. So clearly, cool, we're good. So we can run it. Here's a little program to run it, and we get our output, and we see 4 and 11, 3 and 12, and so on and so forth. So I would claim that this program is correct. It works just fine. Like. I actually have the source code on GitHub, so you can run it yourself and find out. So I think this works. So let's make a bigger program. So let's make 2 drains. And we're going to have one drain move from the first counter to the second, and then we're going to have the other one move everything back. Right? That makes sense. So let's run it. I've got my output, it's saying 411, and I wrote that last week. It's still running. Can anyone see the problem with this code? I mean, well, okay, you probably don't see it on screen, but so we're locking one, or each drain locks the source and then locks the sink and then moves it. So they're both competing, and so they both lock the opposite counter, and then they try and lock the other one, but the other one's not giving it up. So we have a textbook classic deadlock. Writing this program was fun. I was trying to get it to be reliably wrong, and I kept getting incorrect behavior, but not a classic deadlock. So feel free to check out the source code. Now, I think my drain is correct, by the way. But this program is incorrect that uses two little programs. Actually, it uses the same little program twice. So this is the functional programming meetup. So obviously the problem is I wrote this in Java, right? I mean, clearly. So let's write it in Erlang, because Erlang's great at concurrency. Like, I mean, you guys have at least heard the propaganda, I assume. So it's great. So we're going to write it here. So we've got a counter, and let's say we're going to send a lock message to it, and then we're going to allow another thread to send messages to it to decrement or increment it. And it's a little longer than the Java version, but it's Erlang, so it's better, right? I know it's probably hard to read this code, so I'm not. It's all on GitHub, so you guys can trust me on this. I swear I pasted the output exactly. So at the bottom, I have two little pieces of code to start two counters and start one drain, and then I have another one to start two and then start two drains. So we can run this. So we run it on the first one. I didn't get the same debugging output. I changed the messages up, but it runs fine. So then we run it on the second one, and we get two messages, and then it stops again. This code also deadlocks. Even though it's written in Erlang, it uses actor concurrency. It's functional. Erlang does not prevent you from creating deadlock bugs. Now, shared nothing memory is great. I mean, there's a lot of good things about Erlang, but it doesn't stop you from making bugs. And you say, I would never do this in production. If you think about my lock and unlock messages, if you go look at the code, you'll realize, you can do things like this. You can make loops like this, and you would probably not call it lock and unlock, but you can accidentally create the same message pattern. So just something to consider. I think that the problem, so I have a claim, and this claim is that traditional multi-threaded programming, even with Erlang and actor concurrency, does not preserve correctness. So if we have little programs that are correct and use locks to combine them, we can end up with programs that are incorrect. So hope that makes sense. So how can we fix this? So in the late 90s, Simon Peyton Jones and some other very famous people from Haskell came up, actually the early 2000s, they came up with this idea of software transactional memory. And the idea is very similar to database transactions, and you have atomic blocks, and they either execute or they don't, and it can use stuff behind the scenes to do like atomic tests and sets and stuff like this. It got very popular. There have been several libraries created for other languages. But it was implemented as a library in Haskell. So Haskell actually has a library for software transactional memory that you guys can use. So let's roll back and start over. So I have this nice little Haskell program. You'll see these little atomically blocks in there, and it says atomically, and then it calls a function. This is where it's actually draining from both of them. So let's see. So we can run it on one drain, and we get, still works. And when we run it on two drains, it keeps going forever. And since they're both trying to compete with each other, and it's executing reasonably fast, this will run as long as you let it run. There's no deadlock. Sometimes you'll see that the order gets a little inverted and one gets a little ahead, but they're both pretty fast. So now the Haskell code is probably not clear for a lot of you guys. There's this do notation and things like this, and there's all these weird symbols like arrow equals. Haskell programmers call that bind. You won't even see it in the in the first version. So operators in Haskell are just functions. So you can write a function called less than equals in Haskell. You know, but Perl is bad. So we can desugar these Haskell programs. This is the first step the compiler does. It actually just rearranges do notation into a sequence of function calls. So this is the exact same program I wrote in Haskell. You can see it. It's a lot longer. You'll notice that there's a lot of parentheses. So I've actually just demonstrated to you that Haskell is actually a Lisp because it has lots of infernal stupid parentheses. But this is the exact same code, and it's just function calls. Atomically is a function, and you give it a function, and then it does it atomically. And so you can bind this using another function called bind. We'll call it bind. That's what it's called. I think it should be called bind in Haskell, but I don't matter. So this is a great way to write multi-threaded programs. Now you might say, I don't write a lot of multi-threaded code. Obviously I've come up with a big complicated example to scare you guys and convince you that this is important. So I think we're going to look at some simple loops now, because we write 4next loops, right?
Yeah.
Or MapReduce. I mean, this is FunctionalKnox, right? So this is an example you've probably seen several times. You've probably seen it in other talks about functional programming. It's in JavaScript. I know that's your favorite, Nicholas. So we're going to compute the sum of the squares of the list of integers. And so, I've got this version up here with two 4next loops, and of course you can rewrite it as a map function that squares all the integers, and then you can write a reduce function that just adds them up. And it's this nice little 2 lines of code, works great. Well, I don't think it works great. So there's a buzzword I'm thinking of. Come on, you got what's hot nowadays? Big data, right? So let's do this over 100 billion elements. Right? Yeah, sounds fun, right? So you'll notice if you break apart that MapReduce function that there's this map creates another array and then fills it with the values from the previous array with the function applied. So we're going to make 200. We're going to loop over this twice, and we're going to make an extra array in the process. What could possibly go wrong? Right. I mean, so this is not okay. We obviously cannot use this functional code to do a giant MapReduce in JavaScript. So let's make an iterator in JavaScript. And I'm going to make a very simple one. You can come up with a convention for making iterators in any programming language. Some of them have them already. So I'm going to return a pair of values. It'll have one key called value, and it'll have the actual value. And then the other one will be called next, and it'll be a function that gives me the same. If it's null, I'm at the end of the list. If not, this is typical traditional, kind of object-oriented programming, but we're passing functions around, so it's okay. So I have an implementation that uses arrays, and so then I have written an iterative map and an iterative reduce, and so they each take an iterator and they apply the function, and so iterative map, you get one of these iterators back, and so you can just keep calling next to get values, and then you can pass any iterator to reduce, and it'll keep applying it. And so we're writing very primitive code here, so I'm going to actually use a do-while loop, and it's a very evil one with side effects. So so now we can rewrite our program with this iterative map reduce. And it will not generate 2 lists, it'll generate 1, and it will stream over the values so we don't have to pull them all in memory. Because we'll do like AJAX calls behind the scenes, that won't be slow. Of course, most of us at least work, I assume. So, requirements change. So maybe we decide we don't want to square everything. Maybe we want to use a different function. Maybe we just want to sum up the list. Maybe we want to, calculate the maximum value. So we'll replace our specific function with, a generic step 1. But then your boss comes back, and now we're going to do something completely different, and so now we're going to have to pass in, and so we're going to actually just write an iterative map reduce that takes a step 1, a step 2, and an initial value for the reduce, and we're good, right? No, we're not. Actually, even worse, now we want to compute multiple statistics on the list. Maybe we want to calculate standard deviation, so we're going to have to sum the squares and get an average, and oh god. So we're going to write a function called map list helper. It takes a list of functions, and it generates a map function that takes a value and applies each of those functions to it. So we take one value in, and we get an array back. And of course, you'll notice the code here. I'm mapping an array of functions on a value. We can also write a reduce function, a reduce helper that takes a list of reduce functions. And so we're going to need a list of C's and a list of reduce functions and a list of map functions. And we can calculate all of these all at the same time, one loop through the entire thing, and end up with this array of values that's each of the statistics we wanted to collect. And it's good, right? You don't trust me now, do you? I've got a question. Can we always replace our map reduce at the start with this kind of iterative map reduce and using all these helpers, right? It'll always give us the same answer as what we initially did, just more efficiently for big data. No, it won't. I have this function. It's called trust me. It uses this variable called global conspiracy, and it keeps an accumulator, and it keeps mutating these values in this array. So you'll see I've ran it here, and I get, let's see, on the example data I have, I get 625, 261, and let's see, I'm pretty sure I got it. Yeah, I get 2 or 3 different values, and you can play around with this and get several more. And in theory, this should all be the same. I even try resetting the counter. I reverse the array. I get going over the array in a different order will give me a different value. That's fun. So in fact, there's this really clever identity involving map functions. If you map a function over a list and then map another function over the list, you can map the composition of the functions over the list. We can even use this trust me function to break that. It's a classic identity. All of these optimizations, by the way, are called stream fusion because we're taking multiple functions over a list and we're streaming it and we're fusing it into one iteration. So yeah, let's see. So you'll see here, I've got some more examples where I get several different values. Yeah, that big old 4 billion. And then I even get 3 times 4, yeah, 2 to the 25th power. Yeah, this works great. Oh wait, I should go back. So now we did all this in JavaScript, and the problem is JavaScript allows mutable global state. So we can start sneaking state into functions, and this totally breaks this idea of map reduce because we can use global state to make it give us different answers depending on the iteration order, depending on whether we stream it or do it all in one go. We can really screw this up. So we're not going to be submitting any patches to Node.js. We're not going to be rewriting Hadoop and JavaScript because we cannot reliably do this. Turns out in Haskell, the Haskell compiler, because Haskell is pure language, all these identities we want to hold, like they hold true. You can always in Haskell replace 2 maps with a map of the composition of the functions. You can always do that. So that's a standard compiler optimization in the Glasgow Haskell compiler. So that's awesome. Messy, but someone wrote this nice library that reliably will transform all this stuff into efficient map reduces that will always be fused. And so that's just a library in Haskell, and we can trust it, and the compiler will always do this. And that's great. So here's the same function in SQL, and I had it go. I had it do the stuff we were doing earlier, summing and counting and squaring, and I ran it from 1 to 500,000. It took a few milliseconds. And it gave us these nice answers. SQL databases actually, well, most of them, I won't promise all of them, actually have Stream Fusion as a built-in optimization.
Where's the cat?
So if you're using a SQL database, first here's a hint, SQL is a functional programming language. Every SQL database actually has, the good ones at least, have Stream Fusion built in. They can use indexes, they can do all kinds of things, and they can apply aggregate functions to the entire list. If you try and make an aggregate function that has captured state, you'll probably have to at least use stored procedures. You might have to resort to a native interface. You'll have to work really hard to sneak one in. Or you'll end up, it'll complain and say you need to use group by. And then you won't get what you wanted, but it also complained at you. So SQL is a great functional language. It works really fast. So you know, you guys thought this was about algebra, right? Like I was going to come here and talk about algebra, and I've talked about SQL and loops and weird locks that are broken and made some really bad jokes. We've been doing algebra this whole time. We have been combining programs with functions. Some of these functions follow rules. Sometimes we've not followed the rules. Sometimes we've not used good combining functions. And so all of these bugs, at least the intentional ones, are because we weren't doing algebra right. Or we weren't using a tool that would force us to do algebra right. The unintentional bugs are because I wrote this at 3 a.m. over a series of too many days. So let's go back to high school algebra. So there are several properties that you probably learned. One of them is the identity property. So I've written some up here. So if I have an identity in an operation, and we're not talking like functional programming here, we're talking like addition. So like 1 plus 5, you know, not 1 is not magic code for a function. Yeah, I mean the number 1. You know, so that's 6. So 1 plus 0 gives us 1. You know, 2 plus 0 gives us 2. We can swap the order and still get the same thing. So identities just give us back what we started with. I've written this in prefix style as well. And so if you look at plus 1 comma 5 or something like that, plus is just a function. Prefix notation is just a function call. So I've got a function that takes 2 parameters and gives us back a parameter. And so an identity is some value that we can give to this function that will just give us back the other value. So that's all there is to it. Some functions have inverses. We don't run into this a whole lot in programming. It's a value so that I can say, you know, 2 plus -2 gives us 0. It gives us back the identity. You know, 3 plus -3 gives us 0. You know, for multiplication, we'll say, you know, 5 times 1/5 gives us 1. 1's the identity for multiplication. So these make sense. Okay. So we also have the associative property, and this is one I really want to talk about for a minute. So if you have a function that only takes 2 parameters and you want to sum like 20 things, you've got to call it multiple times. So a plus b plus c, you know, and we should draw parentheses around every pair. So like a plus b plus c, you know, and so parentheses around that. So if we rewrite it as a function call, you'll see it's plus, you know, plus a comma b, you know, then comma c. The associative property says that if I regroup these parentheses, so I say, you know, a plus a comma plus a bc, I'll get the same thing as if I say plus plus a comma b comma c. That's all the associative property says. Some people confuse this with commutative property. To give you an example of something that you can work with that is associative but not commutative, think of list concatenation. So I've got 2 lists. I want to concatenate them together. So, you know, I've got a list containing, you know, 1, a list containing 2. So concatenate, have list 1, 2. Well, if I, you know, reorder that, I would get 2, 1. But if I say 1, you know, if I add 3 lists together, it doesn't matter the order, because however I draw the parentheses, I'll end up with the same list at the end. So if I add 1 and 2 together first, you know, I'll get 1, 2, and then 3, 2 and 3, and then a 1 goes in front. So makes sense. And the commutative property is a plus b or b plus a is the same. So 1 plus 2 is equal to 2 plus 1. You know, 5 times 10 is equal to 10 times 5. So that's a commutative function. There are commutative functions that are not associative. Take the midpoint, so a plus b divided by 2. If I say b plus a, I still get the same number. If I take the midpoint of a and b, and then I take the midpoint of that and c, I can fill in some. I have some examples here, and I get like 2 for one, and then 1.5 for the other. So if you regroup it, it's not associative, but it is commutative. So see, then I've got the distributive property. That's another fun one. If you think back, so a times b, a times b plus a times c is equal to a times parentheses b plus c. Like that's, and sometimes things aren't commutative, so we can distinguish a left distributive property from a right distributive property. So addition and multiplication obviously are this way. Let's not think about map and compose on those lists we were talking about earlier. It's not that that's a distributive property or anything. Wait. Let's see. So that's our basic algebra. So if you go look at papers, I'm not going to spend a lot of time on this slide. There are a lot of symbols that show up. There's like this upside down a backwards e, and they mean things like for every, or there exists, or this is an element of a set. And they're great little symbols that show up in math papers and functional programming papers, and they're really simple. This slideshow will be on the web, so it's actually already on the web. So you guys can go and grab this and look this up. And these symbols are not complicated. You can replace them with straightforward English, and it'll make sense. So also in math, we have sets. A set is not ordered. So if we write it in brackets, so like bracket 1, comma 2, comma 3 is a set containing the numbers 1, 2, and 3. The order doesn't matter. So there are operations we can do on sets. We can take the union of two sets. So if I have the set containing 1 and 2 and the set containing 2 and 3, and I union them, I'll get 1, 2, and 3 in the set. You can do intersection. So 1 and 2 and 2 and 3 gives us a set containing just one value, 2. We also have subset. So or is A a subset of B? So 1, comma 2, and then 2, comma 3 for sets, like they're not subsets of each other. But the set containing 2 and the set containing 2, 3, 4, 5, or 2, 3, like those have a subset relationship, and it's not complicated. Most of you seen this before? Cool. Okay. So we've also got set difference. So if I have a set containing 2 and 3 and the set containing 2, 3, 4, and 5, the difference is the set 4, 5. So these operations should be fairly straightforward. And if you've never seen them before, they're not too complicated. You can, they're very similar to arithmetic, actually. Also, we do have the Cartesian product. This one's fun. It's a little different. So what you do with it is you have two sets, and you take the Cartesian product, and you get a set of pairs. So if I have a set containing 1 and 2 and a set containing 4 and 5, the Cartesian product is the pair 1, 4, 1, 5, 2, 4, 2, 5. So we end up with every combination of elements from the set. And tuples, or intuples or tuples, or however you're supposed to say it. This shows up a lot, and it's just an ordered pair or an ordered triple, or 5 things, and it's an ordered list. And so now we're back to list. In math, it turns out we can represent these as sets, and there's some clever nested set stuff that actually rewrites a set that will give us the first and second and third and so on. I'm not going to demonstrate this. It's fun. Basically, everything in math and classical mathematics ends up being reduced to a set. And this is important later because we're going to talk about category theory. So we actually, we can build sets. Like we can say the set of all integers. Z is used to represent integers. So the set of all integers where x mod 2 is equal to 0. Like you could write a set this way, and this will give us the evens. And so you can use all these symbols to write all this down. And then how many of you guys have programmed Python? How many of you guys have programmed in Haskell? Okay. Whatever. How many of you guys have programmed in SQL? Okay. You can write the same set builder notation in all of these. In Python, it's called a list comprehension. Of course, it's an ordered list, not a set. But the idea of applying a list, applying a function to a sequence of values to filter it down. This is a set. This is a list comprehension, or I nearly said set comprehension. In mathematics, this has strong parallels to set builder notation, and the reason it does is because all the people who designed these programming languages knew this and did it on purpose. So it's not an accident that list comprehensions. So I've got this, the set of, I generate the even numbers. You know, I'm going to pretend that 32 bits is enough to represent all the integers. That works. And so I've got 3 expressions on this slide that all give us the evens of that. One in SQL, one in Python, and one in Haskell. So hopefully you can see the parallels. It's being recorded, so you can go back and look later. The slides are on the web. Now let's talk about functions and relations. So a relation in math is a set of tuples. So a binary function, a binary relation would actually have ordered triples. So 1, 2, 3, 3, 4, 5. And this set defines a relation. If you index it and make it unique along one of these axes, you get a function. So every function in math is a subset of some relation. And we can build up the relations that form this. We can build up these relations with Cartesian products of sets. So if I have a function of 2 parameters, the first one comes from A and the second one comes from B, and the results come from C, I can say A cross B cross C. And that'll give me this big relation, and then I can limit A and B to where the function's defined, and I end up with a function. So it's just a relationship with some unique values for the parameters. And we can combine relations, which is actually just like function composition. So we can take, by the way, in a function, A, like the parameters are called the domain. The set that they come from is the domain. So if the parameters are from sets A and B, A cross B is the domain. If the results come from C, then C is the codomain. Reed likes to talk about this. These terms come from math. It's not an accident. So we can combine a relation. And so I've got this expression in set notation here. And so we say, so I've got a function from A to B, and then a function from B to C. So a relation, the composition of 2 relations is finding this common element Y and creating ordered pairs by joining on that. Keep using these words like join and cross join and stuff like that, because the relational algebra is built on this. So if you think about a table, it's a set of ordered tuples. Sure, they have names, but you know, customer ID or 0, whatever, close enough. Join is function composition. Cross join is Cartesian product. All these set union operators, you know, you can union 2 queries. You can also union a query and just selecting the elements from a table. Tables are variables whose values are relations. That's the relational algebra, and that's SQL. And so all of this stuff that we're doing, you've already done it, because most of you said you've done SQL. So I'm going to claim you've already done it. Now, something you might have realized is these functions that I'm talking about are mathematical functions. That means they're pure. That means if I say f of 1 comma 2, and it's a mathematical function, and it gives me 3, I can wait 1,000,000 years. I can run the program 30 times. I can increment a counter 1,000,000 times, and I still get 3. It will never give me a different value. Now, in programming languages, obviously, you know, my JavaScript examples demonstrate we can make functions that will give us a different number every time, even if we give it the same parameter. And we can make all of those functions pure. And what we can do is we can make an extra parameter to every function, and we can pass it the state of the world. So we can put all the global variables in a list, or a record or whatever, and we can make that a parameter. We pass it to the function, and then instead of returning the value, the function returns a new state of the world. So if I have, a function f and a function g, and so I give f a parameter and the initial state of the world. It gives me back a new value, and then I can say the parameters to g with the result of f, and this gives me a third state of the world, and then I can keep doing this over and over and over again. So a function of 2 parameters that returns a value. Now I've got a question. So we were talking about the associative property earlier. Do you think we could rewrite these functions such that they obey the associative property? This is just saying a plus b plus c, f a comma g b c, or f comma g, or f applied to g a b comma c. And that seems a little weird, but I want you to think about this. I'm going to come back to it, but this idea that we could take impure functions, turn them into pure functions. This is called world passing style, by the way. So, and the idea is we're passing the entire state of the world as a parameter, and so it's a style of coding. It's not necessarily associative, the obvious way to write it, but think about it. Now, I want to talk about another property. This one's also useful. It's so we have relationships like less than or equals to, or the modulus function. So if we want to take all the integers, divide them by 5, we'll get 0, 1, 2, 3, or 4, right? It's just someone crack the door. There's all this hot air in here. I don't know whose fault that is. So if we take the integers modulo 5, we can say 2 integers are related if, like, 3 mod 5 gives us 3. 8 mod 5 also gives us 3. So we can say 3 and 8 are related. We could also say 13 mod 5. That also gives us 3. So it's related to 8. Well, it follows some rules. One is that if A and B are related and B and C are related, then A and C are also related by this relationship. Well, what's really cool is it turns out that this divides the integers into 5 sets. And we can give these sets names like 0, 1, 2, 3, and 4. Every integer gets classified into one of those sets. And if we take the union of them, we get back the integers. And these sets are called equivalence classes. Also, generating the equivalence class is called taking the transitive closure. So if I have this binary relation that tells us if 2 things are related, we can start looping over a set. We can say, okay, this is related to that. That is related to this other thing. Okay, put them all in a set and keep doing this over and over and over again. And if we keep doing this, eventually we'll get everything that's related in that one class. And then we can start doing it for the next class. And so you can actually, I'll cheat, this isn't in the slide, but if you've ever heard of common table expressions in SQL and with recursive, like there are recursive common table expressions, you can actually use them to generate transitive closures on a database. So useful fact to remember, unless you're using MySQL, which doesn't have that. So so I've been segueing into this. So I want to talk about abstract algebra. We've got all these properties. We've looked at them on numbers. We've cheated a little bit and looked at them on SQL and other things like that. In abstract algebra, we look at combinations of these operations and we give names to the structures they generate. The thing about abstract algebra is we don't care about the examples anymore. So sure, integer addition, with 0 is associative and has an identity, but we don't care about that. We just care about these structures that are generated, because the cool thing is they all have universal properties. They're invariants about these structures. So they have names like rings, monoids, groups. Some of you probably, if you've had a little bit of higher math, have probably heard these words before. These structures have these universal properties. Any example of that, anything we can prove about groups applies to anything that's a group. So in abstract algebra, we don't care about what's a group anymore. We just care about what we can prove about anything that has the properties of a group. This is the ultimate duck typing. If you've heard, you guys heard duck typing. So these mathematical structures, they have these universal properties. We can combine them, and so we study properties arising from combinations of them, restrictions on them. And this gives us new structures. This gives us rules and properties of any structure that has those rules. And we don't care about the examples anymore. And so I have this quote from the matrix, and it's easy to get stuck on metaphors and things like that. So Neo's talking to Cypher, he's talking about looking at the matrix and code, and Cypher's saying, I don't see the code anymore. Well, if you're used to object-oriented programming, if you're used to some of that school of thought, like metaphors get really popular. In math, we're going to talk about monoids in a minute. This word sounds really weird. We're not going to come up with a metaphor. A monoid just is. A monad, or a category, or a semi-ring, there is no metaphor. They're just a thing that exists unto itself. We can find examples of it. We can find examples of these things in all kinds of programs. That's part of the point of our talk. So do you want to see the matrix in code, or do you want to come up with metaphors? All right, if you've seen matrix, do you want to be Neo or Cypher? Oh, wait. Sorry, that's maybe a bad question. You shouldn't feel bad if you think in metaphors. There's some flawed issues with how high school and college algebra are taught. All of it's building up to see these structures, because the whole reason you're taught all this stuff in school is at some point, 1 out of 100 of you will end up majoring in math for a little while. And all of these properties, like you develop an intuition over the years about things that are like addition, things that are like multiplication, things that are like addition and multiplication together. So we can think in terms of metaphors, but they're very abstract. And a lot of times it's helpful to not worry about this. So let's talk about a semigroup. This is one of those big, nasty algebra words. So we've got a semigroup. And what this means is we have a set, and we have a binary operation on it, and it's associative. That's all it is. So that associative property, so I've got a list of things that are semigroups. So we weren't going to worry about metaphors, but these are all examples of semigroups. So addition and the integers. So 1 plus 2, plus is a binary operation, it's associative, so that means we give it 2 integers, we get back an integer. Multiplication. Multiplication is associative. But let's get into some more, Boolean OR actually is associative. So A or B or C or D or E or F, it's associative. So, we've only got 2 values. In fact, you can actually exhaustively prove that Boolean OR is associative, because you can just list, A, true or false, B, true or false, C, true or false. And then you can come up with this nice table and say, oh, clearly it's associative because every combination of it works. So Boolean AND is also associative. List concatenation is associative. I talked about it earlier, but it is an associative function. So we've got concatenation, which takes 2 lists, gives us a new list, and it's associative. Find the minimum of a pair. So if I've got 2 numbers, A and B, and I take the minimum, and then I take the minimum of that and C, that gives us a new minimum value. It doesn't matter which order I do the minimum in, I still get that. Same with max. Max is associative. It's more fun. Set unions are associative. So if I union 2 sets together and then I union a 3rd set, doesn't matter. Set intersection is associative. So I've got 2 sets and I intersect them, then I intersect that set with another set. It doesn't matter the order I do it in, it's associative. Finding the minimum bounding box to take something that you would do if you're writing a GUI, that's an associative operation. So I've got 2 bounding boxes. I take the minimum box that contains both of them, then I add a 3rd, and I take the minimum that contains it. I'm not going to prove it, but it's an associative function. It doesn't matter if I do these 2 first or these 2, the final bounding box will be the same. Function composition. Function composition is associative, right? wait a minute. Let's put some rules on it. So A, our functions have to be pure, and the domain of the function has to be from A cross A. So it has to be on this set, and then it has to give us a value in this set. So every pair of values that we give it from the set has to generate another value from the same set. It's a little tricky, I realize. So I've got some examples here. I'm using JavaScript again because I want to put some state in there, because if we have an impure function, we can make composition not behave associatively. I called my impure function church because Alonzo Church came up with lambda calculus, and I've got state mixed in it. And so the problem is when you mix church and state, you have problems. Bad joke. I like jokes involving lambda calculus. It's an acquired taste, possibly. So our functions have to be pure, and they have to map every pair of values to a value from the set. So we can't just use any two functions for function composition. So we've got to have some rules. Now I'm going to turn up the. I'm going to make it a little more complicated. So a monoid is another mathematical object. And a monoid is a binary operation, just like before. It has to be associative, just like before. We're also going to have an identity element. So the element, the sets that these functions operate on, there has to be some identity element. So we'll call it 1. So this operation, with the identity element should give us back the other element, whether it's on the left or right. This sounds a lot like a semigroup. In fact, every monoid is a semigroup. This is not object-oriented inheritance. This is better. This is math inheritance. Every monoid is a semigroup because they're both associative. They're both on a set. Monoids have this extra structure, this extra requirement that we have an identity. But that's just an element of the set. So that's a semigroup. So every monoid is a semigroup. That's great. This is a whole lot better than every cat is a mammal, right? These words don't even make sense. So it turns out a lot of semigroups actually are monoids anyway. So I've got the examples from the previous slide. So addition, 0 is our identity. Multiplication, 1 is our identity. Boolean or, let's get it backwards. False is the identity for Boolean or. False or some value gives us that value. True is the identity for Boolean and. For list concatenation, we've got the empty list. So I have a list with 0 elements, and I concatenate it with another list. I get back the list I started with. The minimum function. Wait, this feels a little complicated. So what's a number that I could give to the minimum function that will act as an identity? Positive infinity, right? That works. I feel a little uncomfortable with infinity, but the minimum of positive infinity and another number, that's the number we started with, right? So for maximum, we could use negative infinity if we're going to play this game. Oh, do you trust me? What about unions? The empty set is the identity for set union. For intersections, we're going to have the set of all possible sets, right? Some of you, this is going to bother. The rest of you, this will bother in a few minutes, or possibly late at night when you start thinking about God, the universe, and everything. Function composition is not a trick question with this one. The identity function is our identity. I guess that's why they called it that. So if I compose the identity function with another function, I get back the function I started with. Doesn't matter the order. So let's talk about identities. If you start treating infinities as actual numbers that you can manipulate, this causes some problems in math. And when I say problems, it doesn't cause problems, but you start accepting some very interesting facts. You invoke something called the axiom of choice. Religious wars were fought over this in the early 1900s, and they still are. If you ever hear of intuitionistic mathematics, this is part of the Holy War. So let's not use positive infinity and negative infinity. Let's make an element called top. It means nothing. It's just an arbitrary thing, and I'm going to define top such that the minimum of a and top, or top and a, gives us a. So I'm going to use that as an identity for min, and then I'll use an element called bottom for max. Max, a, and bottom, and mathematically we represent them with this kind of funky t and an upside down t for top and bottom, because see, it's upside down, so it's bottom. Mathematicians are horrible people. So these aren't positive infinity and negative infinity. They kind of work like it, but we're not using that. We're not using that against us in this particular case. It's just an arbitrary element, so we're going to add it to our set, and we're just going to say the identity. This is the identity element for our operation, and it's good. It's cool, right? Turns out you can do this with any semigroup. You can extend any semigroup by adding an arbitrary element and saying we're going to define the operation with this element such that it's an identity. I mean, we would never do this if we were calculating a list from a database and we use, a very negative, timestamp as minimum to get the maximum when we're selecting records, right? In fact, wouldn't it be awesome if SQL let us add, like, make a new type where we could add like this element to it? Oh, wait, using Postgres again. Sometimes null gets roped into this, except null can mean anything and everything in most programming languages. Hoare called it his billion-dollar mistake. Some people think that this was, a bit, modest on his part, and trillion might perhaps be a better, sum. So this set of all possible sets, I'm going to come back to that because this really. Oh, well, I'm going to come back to that in a minute. So I want to talk about a quotient monoid. So we talked about the integers modulo some number. Well, we can come up with relationships on monoids that split them into groups. And we can use this transitive closure operation to generate equivalence classes on any monoid, as long as our function obeys some rules. And one of those rules is that the operation on the monoid should be preserved. So if I say a plus b, then when we divide it into classes, the class for a and the class for b should also result in the same thing that we would have gotten. So this should distribute. This function that we're going to use to generate the equivalence classes should preserve the operator, the relationship among elements between the operator. It should preserve the identity element. And the domain and codomain of the function that maps them should actually be A and B, the stuff we're starting from. And we can generate new monoids from this existing monoid, and we're going to call it a quotient monoid. So when I said we could relabel, we could call the equivalence classes 0, 1, 2, 3, and 4. This is an example of generating a quotient monoid from the integers. So you've heard of divide and conquer. Well, you can actually use divide and conquer with monoids. And this isn't the same as divide and conquer. This is translating your problem into a new space using some kind of quotient and get a simpler solution and then back translate it with some effort. So this is actually a fun pattern. I want to talk about lattices a little bit too. This is not a monoid or a semigroup. We can have this so we've got less than or equal to on integers. It relates numbers too. It's not an equivalence relation because, well, it doesn't divide it into sets. But we can so remember top and bottom? We can define them in terms of, we can put those as, so less than or equal to, top, but, and then bottom. And so these put bounds on it. So I'm going to run a little fast. So the cool thing with this is we can start thinking about types. And so we were talking about subtyping earlier. object in an object-oriented language is called top. Every subtypes form a lattice. So A is a subtype of B. A is less than or equal to B. You can have a type called void in languages like Haskell that are inhabited by 0 values, and void is a subtype of every type, so it behaves like bottom. So you actually have this nice lattice of subtypes where we've got the subtyping relationship actually acts like less than or equal to on the integers. Now, it doesn't order every type. Not every type is related, but we can actually, we can model subtyping with a lattice, actually. And if you look at a lot of papers, you'll see a less than with like a colon as the symbol for subtyping, and that's a lot like less than or equal to. And so that's why this symbol is chosen. And so now I want to take a brief digression, like I've been doing all day. So way back in 1890, this guy Cantor came up with a proof. And he said the natural numbers, like 1, 2, 3, 4, and 5, are the same size as the integers. So 0, 1, -1, 2, -2. So he connected these sets and said, okay, every natural number I can map to an integer. And so people are okay with that. So then he mapped all the integers to the rational numbers. Rationals are ratios of integers. And so he came up with these charts, and he did this little thing called diagonalization. And so there are as many rational numbers as there are integers. Okay. And then he took the reals. So the real numbers include irrationals like pi, the square root of 2. It can get tricky to define the irrational numbers. And so there are an infinite number of integers. There are the same number of natural numbers as integers. There's the same number of rational numbers as integers. The reals, however, there are way more reals than there are rationals for integers. So I've got this set that has an infinite number of things in it, and I've got this other set that's got more infinite things in it than this other set. And people said, that's not a proof. And other people said, that's actually a really cool proof. And so this started a crisis in mathematics. Other people contributed to it, but Cantor definitely played a role because people are like, tabs versus, this is a proof, this isn't a proof. And so a bunch of people started a process to formalize all of mathematics. You've possibly heard of Bertrand Russell and Whitehead's Principia Mathematica. This was a project to formalize all of mathematics on the basis of set theory. And so Russell had to start dealing with this idea of a set of all possible sets. Does that statement make sense? And so he came up with the first type system to resolve this issue of the set of all possible sets. So we've got sets that don't have subsets, or that don't have sets within them as elements. And so you've got these ranks of sets. And so he actually came up with a type system. And this is one of the modern type theory. Actually, if you go back, you can trace a lot of roots to his work there. There's way other stuff that's gone way beyond that. But the first type system in kind of a formal mathematical sense was for this. Then there was this guy called Kurt Gödel. You possibly heard of Gödel-Escher-Bach or Gödel's incompleteness theorem. So he was doing some work, and he was writing letters to Bertrand Russell, and he was saying, I think there's some issues here. And so they were trying to say every statement in mathematics can either be true or false. And we're going to formalize all this, and we're going to have it all written down. And so he said, I think there's some unclassifiable statements. You can't prove them true or false. This is actually directly related to the halting problem. You can't decide if a program halts or not. In general, you can in specific cases, but that's for another talk another day. So Russell said, this is pretty interesting. You've kind of destroyed the whole point of my project, and so it's kind of completely worthless. Now, this is really awesome math, so you should keep working on that. Bertrand Russell was a great guy. Some famous people in the open source community could take some examples from him. So Gödel ended up proving this really famous incompleteness theorem. Alonzo Church and Alan Turing were also doing work on the foundations of mathematics, trying to work on the notion of computable functions in a math sense. And so this all kind of forms the basis of modern mathematics, trying to answer, is Cantor's proof a valid proof? And, you know, infinity is problematic. Sets of all possible sets, these statements like this are very problematic, and they cause a lot of frustration. And so kind of the great mathematical project of the early 20th century was to sort this stuff out. And some of these answers have very, very huge implications for computer programming and functional programming. So this is going back to the formal stuff. This isn't entirely related, but so one thing you can talk. So another algebraic thing we can talk about is fixed points. I want to take a break with some history. So the idea of a fixed point, you shouldn't worry about it a lot, but it will come up in functional programming literature. And so if I have a function, like on the integers, a fixed point is a value x where f of x is equal to x. So the identity function, every value is a fixed point of the identity function. So f of x equals x. That's the definition of the identity function. So every x is a fixed point. If you think of a parabola, you know, x squared, 0 is the only fixed point of it because 0 squared is 0. So this works on numbers. Turns out it also works on functions. You can find a function that acts as the fixed point when a function is applied to it. I'm not going to derive this. I did it once with undergraduates. It took about 3 hours. They all mutinied on me. Clearly, I learned my lesson because here I'm giving talks on abstract algebra again. So this function, this fixed point, that's a function, not a number, has a name. It's called the Y combinator. And so Paul Graham is responsible for all of functional. So we can use fixed points. It's even more bizarre. We can use it to define recursive functions without resorting to names. Like I've got 2 examples here. Got the Fibonacci function, and it refers to itself in its definition. I've got some recursive data types of a tree. So the node of a tree is either a value or another tree. So these definitions, use the definition in the definition itself. We can actually use the fixed point function, the Y combinator, to define recursive functions. I'm not going to demonstrate that right now. I'm telling you this because someday you're going to read a paper and someone's going to talk about this, or Paul Graham's going to pitch a startup, and you're going to get really excited. Which, by the way, Y Combinator is a company that bootstraps other companies. So it's a recursive company. So that's the joke.
Huh.
That really is the joke on us. So we can use. You don't actually have to worry about this because every compiler writer learns this, because when you write a compiler that generates code for Fibonacci or recursive definitions of trees, the compiler writer used fixed points to generate the code. So you don't have to know it 99% of the time. So it's fun, not for today. So now I'm going to jump to category theory. All of the stuff I've been talking about has been from abstract algebra. Category theory was developed by algebraic topologists. I'm not even going to try to define for you what algebraic topologists do. I had an algebraic topologist as an advisor, and I'm still not clear on what he did. So I asked him about category theory one day, and he said, well, it's generalized abstract nonsense. And my first thought was pot me kettle. So category theory, now mathematics, everything gets reduced to a set in classical mathematics. In category theory, we start talking about functions that map between categories. So in normal math, sets are an undefined notion. We don't define what a set is, we talk about their properties. And so we have some axioms. Zermelo, Frankel with the axiom of choice is a common set of axioms about sets. And so all of classical mathematics works in terms of sets. Category theory actually can be used to redefine all of mathematics in terms of functions as a central undefined notion. Now, a category theorist would be spinning in their grave right now. Since most of them are still alive, this is an especially contradictory problem. So functions are left as this undefined notion for category theory. And we can rebuild all of mathematics on functions. And we're here today talking about functional programming. Category theory has gotten very popular with functional programmers. And so algebraic concepts like monoids can be rewritten in terms of category theory, which takes us back to the quote at the beginning about monads. A monad is just a monoid. So we're talking about a set with an associative function that has an identity. A monad is just a monoid on the category of the endofunctors. Well, functors are functions that have the same domain and codomain, so it's a monoid where the set is functions instead of numbers. Now, monads also have nothing to do with side effects. However, monads do, because I was talking about recasting role passing style in terms of associative function. You can use it to order things. Each pair of actions that we do action 1, then action 2, then action 3. We can reduce each pair in any order we want, and the state will end up waiting on state, but we can actually thread it through these functions. And so a monad can be used to abstract I/O, because I/O is a side-affecting thing. So in Haskell, they use monads. So we like to make fun of the gang of 4 because it's functional programming, and algebraic programming is the devil. And so, we don't have any patterns like monoids and semigroups and monads to structure our program. So abstract algebra is actually about composition of structures. Category theory is that times 10. It can be very confusing. It's called generalized abstract nonsense for a reason. This is not to be a disclaimer, but you can learn a lot about programming by studying it. However, it's built on these ideas from algebra. Category theory is very algebraic. It's about composition. It's about building things out of components and preserving structure. Well, a structure in a program that we would like to preserve is correctness. So if I have a function and another function that are both correct, I would like to combine them in such a way that the whole thing's still correct. That's a structure that I want to preserve it. Maybe you guys don't. I don't know. Maybe you get paid per bug. You probably don't. You do get paid per bug. So if you go look at the monad, so Haskell is not a perfect language. You can implement monads in Haskell, and it's got these functions and it's got these monad laws. And so if you look at it, if you go to the Haskell wiki, the Haskell compiler can't prove that your function follows these laws. So you end up writing some functions for a monad, and you have to prove that it follows the monad laws. Well, if you look at them, I've got this function return and this function bind, and so zeros in it. So return gives us back this function g. So it's like an identity. In fact, it's a commutative identity because you see the order there. And then here we've got this thing called Kleisli composition, which looks like the associative rule. So monads are just a monoid in the category of the endofunctors. Makes sense. You guys are good now, right? No. So this is great. I think, like I said, so category theory is something that you should study if you want. If you don't want to study it, you can still be a great functional programmer. You can actually go study abstract algebra and apply a lot of this without resorting to category theory to your programming. You can use it to learn what's wrong with state in your JavaScript programs, how to write better SQL queries. It's a great thing, but if it's stumping you, don't let it hold you back. But I hope this talk has demystified some of it for you. And so I want to talk, this is my last slide that matters. So there's a paper called Can Programming Be Liberated from the von Neumann Style? A Functional Style and Its Algebra of Programs. This paper was written by John Backus. If you've heard of Backus-Nairn BNF, it's that John Backus. He also helped invent Fortran and Algol. So computer science, LACIOM in 1977, so like 39 years ago, almost 40 years ago, gave Backus the Turing Award, which is like the Nobel Prize for computer science. And so he wrote this paper about an algebra of programs and a functional style. And if you look through the table of contents, you've got stuff about managing state, applications of functions. You've got a factorial function as an example because some things never change. There's a whole chapter about, let's see, there's a whole chapter on there's a whole chapter that basically sounds like Let's Invent Erlang, actually. And this paper, like half the stuff about monoids and identities and stuff like that show up as like paragraphs in this paper. So I'm sure we've all been told that programming moves really fast, no one can keep up. If you took this paper and slimmed it down better than I have, this is not a presentation of this paper, but a lot of this stuff shows up in that paper. Category theory hadn't been applied yet, but it came to bear on the problems he predicted. Problems of I/O and state, which he was already talking about. This paper, you could present this at a conference now and claim you wrote it yesterday, and a lot of people in the room would be like, wow, this is awesome. I've got to keep up with this. And it was written 40 years ago. So I've presented a lot of elements from it, this idea that we want to reason about programs. We want to build them from smaller parts, and we want to have operations for combining them that preserve structures, that maintain invariance. I'm sure we've heard about maintaining invariance in classes if you took any. This is what we're trying to do here. And algebra can tell us a whole lot about things for combining stuff. It's about composition. It's about operations that preserve structure. And that's 90% of what you're doing in abstract algebra. You're studying what things are preserved, what kind of operations will preserve a structure, and what kind of rules they have to follow. That we broke in those first two examples repeatedly by having impure functions. Locks. The software transactional memory in Haskell is a monad library. So atomically is a component of a monad for transforming state. So all of this stuff that we were doing about algebra, a whole lot of that first two slides was distributive laws, associative laws, composition of functions as a monoid. That's everything we did wrong in those first two slides. So I'm done. I hope I haven't left everyone totally confused. If anyone has questions, I'm happy to take them. I have a slide of references. Again, this will all be on the web, so you guys can catch it that way. But if anyone has questions, I will try to answer them. I'm not the world's best mathematician. I should go ahead and disclaim that. But I hope this has made sense. I hope this has helped increase some understanding or added some clarity or giving you the courage to go read some more about functional programming. So.